Welcome to Oddly Real. I'm Nem Stefanovic. We live in an electrified society. Electricity powers our lighting, home appliances, computers, televisions, and so much more. The basic premise behind the technology is that electrons can be pushed through conducting paths like wires, and that energy can be harnessed for practical use. In fact, the transmission of power works over great distances like hundreds of kilometers. Yet, even with optimal design and engineering, we can't avoid losing a few percent of the overall energy due to resistance and heat loss, which is inherent to the transmission cables. However, a discovery was made over a century ago that certain materials lose their resistance to electrical flow under certain conditions, such as extremely low temperatures. We call these materials, in this condition, superconductors. They have the very unusual effect that if you set their electrons in motion, the electrons continue to move without any resistance or heat loss almost indefinitely. The electrical currents will continue without the need for any additional energy. They also exhibit other fascinating properties as well, such as magnetic levitation, which we will discuss later in this episode. In order to understand superconductors, we'll start by understanding ordinary conductors of electricity. Electricity is the net flow of electrical charge. For example, the electricity from the outlets in our homes is due to the flow of electrons through wires. We also call this an electric current. Some materials, like the wires in our house, allow electrons to flow through them very easily. We call these materials conductors. Conversely, there are also materials that inhibit the flow of charge. These materials are called insulators. Metals are really good electrical conductors, generally, whereas ceramics are generally poor conductors. Why are metals good electrical conductors? It has to do with their atomic structure. Electrons are arranged around atoms in shells and subshells around the atomic nucleus. The outer shell, which is furthest away from the atomic nucleus, is called the valence shell. Even a small amount of energy can elevate the electrons into higher energy states and provide them with energy of motion to move around the conductor. In fact, they are so free to move around that they can go anywhere within the metal sample. It's like the metal consists of atoms that are surrounded by a sea of electrons. We can instigate the movement of electrons within a conductor by supplying energy via an electric field. When an electron moves within a conductor, the nuclei of the atoms, which have positive charge, attract the negative electrons and get in the way. The electrons experience a series of collisions with the atoms in the material, which results in their path being deflected in random directions. This impedes the motion of the electrons. There's a resistance to the electron movement. In the presence of an electric field, despite the continual collisions and random redirections of the electron motion, the electrons will be nudged to drift a little bit in the direction opposite of the electric field. Thus, overall, there is a small electron drift in one direction as the electrons travel through the conductor. If there was no electric field, the electron movements would be totally random, not in any particular direction, so there would be no net current. Interestingly, electron drift, under the influence of an electric field in a conductor, is very tiny, in the order of millimeters of distance traveled per hour. But if the drift speed of electrons is so slow, how does electricity work so quickly to turn on a light? Even though the actual drifting of the electrons in a direction within a metal or a material is slow, the forces felt by the electrons due to the electric field happen at almost the speed of light. The forces felt by the electrons via the electric field are like a pressure that is trying to push the electrons forward in one direction. All the electrons in the conductor feel the force of the electric field almost all at once, including electrons present in the filament through a light bulb. Ultimately, to keep electrons moving in one direction, it requires energy to be continuously applied to them, typically in the form of an electric field. This field can be set up as an applied voltage from an energy source like a battery or even a distant power station. When electrons travel, the collisions of the electrons in the atoms of the material transfer energy to the material in the form of heat. Thus, the material increases in temperature and energy is lost in the form of heat. This hindrance of movement and loss of energy is what is called electrical resistance. Additionally, the resistance of a conductor increases with increasing temperature, since the atoms within the material vibrate and move around more to further resist the motion of the electrons. It's this last observation that inspired people to investigate the electrical conductivity of materials when temperatures are lowered. Lower temperatures typically mean less resistance and easier electron flow. The lowest possible temperature is called absolute zero, which is 0 degrees Kelvin, and it represents the minimum amount of energy that a substance can have. In one experiment, it was found that the element mercury, when cooled to 4 degrees Kelvin, or 4 degrees above absolute zero, had 0 electrical resistance. A material that has no electrical resistance is what is called a superconductor. Very quickly, it was also discovered that there were other materials that also possessed these properties at sufficiently low temperatures close to absolute zero, such as lead, vanadium, aluminum, titanium, and even alloys like indium nitride. Superconductors have some fascinating properties. Primarily, a zero resistance to the flow of electrical current means that if an electron is forced into a current motion in the material, it will continue its motion without any additional energy needing to be supplied. The electrical current can flow continuously, with experimental measurements indicating that the current would be present for 100,000 years or more. The electrons would not collide with the atomic molecules of the substance, and they would not lose energy to heat. Another amazing property is something called the Meissner Effect. A superconductor blocks magnetic fields from penetrating its interior. A regular conductor would allow magnetic fields to pass through it, in some cases concentrating the magnetic fields and in other cases causing them to spread out. In the case of superconductors, the exclusion of magnetic fields result in very strange effects, like magnets being able to hover over the superconductor due to the repulsion of their fields. When a magnetic field is applied to a superconductor, current loops are generated within the superconductor that produce opposing magnetic fields that then cancel out the applied magnetic fields. Additionally, these opposing fields also produce a repulsion effect against the magnets near the superconductor, causing levitation. It turns out that there are limits to these behaviors, since a strong enough magnetic field will overcome the Meissner effect to penetrate the substance. In this situation, the substance will lose its superconductivity. It's interesting to note that moving charges in a current, even within a superconductor, also produce an inherent magnetic field of their own. Thus, there's an upper limit to how much current a superconductor can carry, since at some point the magnetic field of that current will grow large enough to disrupt the superconductivity of the material. There are multiple factors for this situation to occur, including the material itself, the superconducting temperature, and the material size. What exactly happens in the material that makes it a superconductor? How can an electron all of a sudden experience no resistance to motion when it moves through a material? This is due to quantum mechanics. First, each particle has a characteristic momentum, which we call a spin. It's not necessarily that a particle is spinning, but it's a property of the particle. For example, electrons have a 1/2 spin. Particles with half integer spins are called fermions. Conversely, bosons are particles that have whole integer spins. The laws of quantum mechanics require that fermions with half integer spins are limited by how many can occupy a certain energy state. This is not the case for bosons, which do not have limits on the number that can occupy an energy state. Additionally, the nuclei of atoms vibrate. When multiple nuclei vibrate at the same frequency, the energy associated with these vibrations are called phonons. Superconductivity is explained by the BCS theory. An electron can distort the molecular structure of a conductor to create a short-lived positive charge. Another electron is then attracted to the positive charge. The two electrons can combine to form a Cooper pair. Due to the lower temperatures in superconductors, there isn't enough energy to separate the electrons, so they travel as a pair acting like a single particle. Additionally, the two electron half spins also interact, producing an overall spin that is an integer, allowing the pair of particles to act like a boson rather than a fermion. Thus, many Cooper pairs can collect together into a single energy state, or condensate, just as bosons would behave. There are many Cooper pairs, and in this state, atoms would have to interact with all of the pairs simultaneously. This results in atoms being less disruptive for electron travel, and electrical resistance essentially disappears. Interestingly, in the search for new superconducting materials, it was discovered that metal oxide cuprates could also be superconducting at temperatures higher than metallic conductors. Metal oxides are normally insulators, not conductors. In fact, in 1986, copper oxide cuprate was found to become superconducting at 35 degrees Kelvin, much higher than other materials. Since that time, even higher temperatures for superconductivity have been achieved at around 134 degrees Kelvin. The quest continues to discover materials that may be superconducting at room temperatures for practical applications that don't require special cooling systems. One thing to note is that there are still some other practical considerations as well, like ceramics, unlike metal conductors, are brittle and can't be drawn into wires very easily. Additionally, mechanisms for superconductivity in the record-setting doped cuprate ceramics also can't be explained with traditional BCS theory. So there's still a lot more work to be done before all of the benefits of superconductivity at higher temperatures can be unlocked. Finally, superconductors do have real-world applications today. For example, MRI machines need large, powerful magnets to operate. Superconductors are used and fulfill that requirement well. Also, particle accelerators like the LHC need powerful magnets to control particle beams for the purpose of collisions. Superconductors are also used in the particle detectors as well, which then feed that detector data to computers for analysis. Finally, SQUID devices, or superconducting quantum interference devices, use the principles of superconductivity to detect extremely small changes in magnetic fields that can detect up to 16 orders of magnitude finer than the fields of refrigerator magnets. I hope you enjoyed this episode, and remember, oddly real, really interesting.